In this video, I want to prove the result that you see here on the whiteboard. It seems quite complicated, but as we will see, the proof is not difficult. In particular, if you assume that A and B are two scalars, so they are not operators, then all these commutators here will be zero, and you get a trivial result, which is this result here. So in this case, you know that since A and B are scalars, the exponential of minus A can move to the left of B. So we have xa times x of minus a, which will give us b. And of course, this is equal to b. So simple as that. But in case a and b are operators, then we need to be careful because they do not commute anymore. Now, let's start from defining the following function, f of t. T is a certain variable, it's a scalar. You can think of that as time, but it is a continuous variable. And then we define e to the ta b e to the minus ta. So you can see that we get this expression here when we set t equal to 1. So we will be interested in this point here, t equal to 1, later. What I'm going to do now is I'm going to take the derivative of this function, so f prime of t. When I take the derivative, we have a product of functions, as you can see. So first we take the derivative of this, which will give us a times all this quantity here, which is f of t. And by the way, a commutes with this operator here. So we can write it like this, or if you want, we could also have written it in the following fashion: e to the ta, ab, e to the minus ta. You can show that this coincides with this because these two operators commute. Then we also have to take the derivative of this part, which will give us a factor of minus a, so I can put the minus here, but you have to be careful because a appears on the right this time. And here we have f of t. So basically the derivative of f of t is equal to the commutator between a and f of t. Now at this point, we are going to expand the function f of t in a series, so we are going to write it in the following fashion: c0 plus c1t plus c2t squared plus dot dot dot. You get the idea. So the derivative f prime of t is equal to c1 plus 2c2t plus 3c3t squared plus dot dot dot. So this, which is equal to f prime of t, should be equal to the commutator between a and f of t, which we can write in the following fashion. First, we have the commutator between a and c0, which is a constant with respect to t, but it is still an operator because we started from an operator. F of t is an operator. It's a function, but it is an operator function if you want. Then we have the commutator, so plus commutator between a and c1 times t, and then you get the idea. You also have plus commutator a c2 t squared plus dot dot dot. And at this point, you can see that c1, which multiplies t to the power 0, so that's 1, we have that this is equal to the commutator between a and c0. And then we have 2c2 equal to the commutator between a and c1, and then you get the idea. You have 3c3 equal to this, and so on. Now, c0, if you check, is equal to f of 0 from here. But f of 0, if you remember the definition given here, is equal to b. So basically, we have found that c1 is the commutator between a and b. Then, from this equation here, we get c2 equal to 1 over 2 commutator between a and the commutator between a and b. And then in principle you can go on, and let me tell you that These two here, we can recast it in the following fashion for convenience: 2 factorial. C3, if you think about it, so we have 3C3 equal to the commutator between A and C2, and C2, as you can see, is given by this expression. You can see that we get 1 over 3 factorial, so when you divide by 3, you also have a factor of 2 here, so you get 1 over 6, which is equal to 3 factorial, 1 over 3 factorial, and then of course you get the commutator between A and the commutator between A and B. So it's some kind of nesting of these commutators. They are nested commutators, and so on. So you get the idea, and basically you can calculate all these coefficients, and at the end of the day, you get to this kind of expression here, which seems complicated, but as you can see, the proof is not difficult.